Hi everyone, so welcome in this second part of the devlog number 29. In this part, we will be focusing mostly on the log manager implementation and the various improvement that we made on this class, mostly using the concurrent queue model now from MoodyCamel. Using this, you can in fact delay the execution of the writing of your log messages to another thread actually, and you can then improve the performances that you get in the threads where you are performing actual work. So yeah, without further ado, let's try to jump into this. We'll start with reviewing a little bit what kind of performances improvement you can get with and without log messages, and then we'll go deeper into the different changes that I made. Let's go. And what was I mentioning before that? Yeah, this was what I was talking about concerning the change in the log manager, where we have only 250 microseconds without log messages and so on. And this is the part that I just started to talk about. So we are focusing on this part, which is the part which is executed when we use a log thread part. And so the log thread here, as I said, is going to support taking multiple messages, because on the other threads you can be bombarding your queue actually with a lot of output that you want to display, and it's actually more efficient to take all those outputs, I mean a good share of them, many of them at least, try to concatenate them in memory into a single string, and then use the string to display what you want in the standard output, or to write that into your file. So you're actually saving some waiting, because accessing a file is pretty slow. Displaying on the standard output also is slow from the initial test that I did, at least. So you want to reduce this operation if you can. So what we do here, we're going to loop continuously, and we use this wait DQ bulk time, and we wait for 200 microseconds, and we try to retrieve different outputs. We can retrieve as many as I think the current value I use is 1024. I don't know why I put 1024. I could just put 1000, but I like power of twos, I guess. Anyway, so once you have collected those outputs, you're going to sort. I mean, this is something I added later. Yeah, because there's one issue with the concurrent queue, which is that you can push data indifferently from multiple threads on one side, and then on the other side, when you try to collect the data in a bulk way, so you get all of them together, you don't really have an order for those messages, depending on which thread the message came from. So without this reordering operation here, I could end up with a display that was a bit inconsistent, because you could have one thread displaying a message at time t1, another thread at time t2 with t2 slightly bigger than t1, but on the other side of the queue, when you were retrieving those two messages, you could get those two messages flipped, and then you could display t2 before displaying t1, and when you log that in a file, it doesn't seem very consistent to have your time going backward. So what I added then was to add a specific tag. I guess it's actually just a single number and an integer value right here, and this integer is continuously increased, and whenever you need to generate a new message, you're going to increment this integer value atomically, which means that all the threads are going to have a single ID which correspond to a time tag, basically. And this time tag is also sent as part of the message that you want to log. And then when you retrieve the bulk of all those messages, you're going to order them by time tag. And then this is solving this issue that I mentioned with inverted time values. Anyway, this is not something I did at first, so we should not really focus on that. Maybe I should just focus on the code here. But yeah, the other part, another interesting part, I think, is that I want to keep control of the memory allocations. And if I were to use just a simple string, for instance, the problem with the strings is you are relying on the C++ library itself to do the allocation for your string, and whenever you want to write something to that string, you might have to grow the memory allocated for that string, so do another allocation. And if you are logging continuously in your project, if it's a game engine and you are going to write data continuously for every frame, you might end up reallocating strings continuously if you do that. So what I did, one of the first thing I did was to use this get output string, which is going to create a single output string per thread. And okay, I should probably not show that right now because I also updated this part at some point. And initially I was using a simple map of thread ID to a string, and this would allow me to allocate a string only once. And then this was the string I was using to write data. And the thing is, what I'm doing here, as you can see, I retrieve the string, a reference on the string, and I every time I need to write something in the string, I first reserve the data, I clear the string, and I will write the data. So when you do that, you might increase the allocation for your string if it's not big enough to hold all the data. But the point is, you keep using the same string, which means that the next time you have to iterate on this code here, your string will already be bigger. So eventually your string will grow, the buffer for your string will grow, and it will reach a point where you don't really have to do any allocation anymore dynamically. You can just keep using this large buffer, which would probably be larger than needed most of the time, but at least you keep reusing that continuously for every frame, and you don't need to reallocate continuously. So this was the basic idea. Then yeah, when you start using a concurrent queue with that, the other part of the idea was, okay, I get the string for the current thread, and then I'm going to move the string into the queue. When you move the string, you are effectively taking the memory allocated for this specific string, and yeah, you don't make any copy of this memory, you just encapsulate that into another string, which is the one which is posted on the queue. So you're going to use that on the other side of the queue itself, so in the logger thread. And when you do that, technically, the next time you need to write a string from this thread, you don't have this memory available anymore, so you can't really, you have to do another application. So the other part of the concept was to introduce another queue, which is this one here, the recycle queue. And the recycle queue is doing the opposite of the message queue. Message queue is used to send a string to the logger thread. But then on the logger thread, you're going to collect the string, again, avoiding allocation, and you're going to concatenate them into a big buffer. Once more, this big buffer is kept into the thread, the main entry point function. So it will be growing progressively, but at some point it will be big enough to hold any kind of input that could come to this buffer. So you will not need to do memory allocation continuously, rebuilding a buffer from scratches. This I can show you here. You just add the string, which is a buffer, and the buffer is going to be extended whenever we need to do, whenever we realize that the current capacity of the buffer is less than what we want to put in that buffer. So we will have a few of those messages growing the buffer progressively, but at some point you don't have those messages anymore. And yeah, that's it. So what we do here is we take all those input strings, we use them to fill the buffer, and then what we can do is we just send those strings back on the recycle queue. So the idea was to take the memory for those strings and then just send this back on the recycle queue. Then the next time you get to the point where you want to write a log message, first thing you would do would be to try to figure out if there is anything on this recycle queue, because those would be incoming string payloads, if you want. And sometimes you may find one, and sometimes you may have no pending element on this recycle queue. If there is one pending, you take it, and when you take it, you actually get access to the already allocated memory for that string. So when you do that on any given thread, this actually becomes the string you want to use right now on this thread. And you just keep doing that continuously. You check if there is currently enough memory allocated for the string. If it's not the case, you're going to increase that. But again, this string itself is going to go on the message queue, then come back on the recycle queue, then go again, then come back again. So eventually the allocated memory will grow to a point where you don't really need to do any allocation anymore to put whatever you want to put in the string. So you have a few strings like that are in flight, if you want, and the number of strings in flight could technically grow a bit, but you could eventually reach a point where you have so many threads, so many string in flight, and that you always have one pending on the recycle queue, and you can always pick that one to send a new log message. So yeah, this was the initial idea, to try to avoid any kind of dynamic allocation in the log manager. Point is, that was not really quite working as I thought it would work. We'll come back to this in a moment. Yeah, so this is where I did some tests to try to see if I was growing the string progressively, and if it was using different string or not. I was not really fully understanding what I was doing initially, but yeah, what I realized was later that I had a problem, and this problem was here with the enqueue bulk, as far as I remember, right? But anyway, first thing I realized was doing it this way, you could indeed reduce significantly the time needed to process some tasks, because in fact you're not really displaying anything anymore from the different threads where you're executing the task. What you just do is you generate a string, which is a message you want to display, and you post that, and the message display itself will only occur a bit later in the logger thread. So on your main thread, once you have posted your message, you don't need to worry about that anymore. So you're saving a lot of time not waiting to write the data into the standard outputs or into your log file. So as I said here, for instance, executing 10,000 tasks, taking like a bit more than 1 second first, 1.4 seconds, and now I was down to only 29 milliseconds, which is, I think it's something like a 50x decrease of the time taken. Then I was continuing with some additional tests, unit tests, because at that point I was still working on the task graph implementation, doing a few different things like that. And what did I realize at this point? Let me see. Yeah, that's where I realized that I could have mixing orders for the outputs, like this one, because I was testing on the, just here actually, I was testing on the task graph, and the task graph is really about ordering tasks with dependencies between them. So what I have here is the first number here is some kind of layer, if you want. So I have first layer of task, and then a second layer, then a third layer, and so on. And this unit test was constructed so that every task from the second layer, for instance, would depend on all the tasks from the first layer, which means that before you can execute any of the tasks on the second layer, all the tasks from the first layer must already be executed, which means that all the tasks 0 something should have been executed before any task 1 something. And as you can see here, you could get a display of the output for task 1 before the task 0. And if you look at the time, here you would see that actually, yeah, task 1 was after the task for layer 0. But the ordering here was incorrect, because on the logger thread, we were taking a bulk of multiple output messages together, and we were not really reordering them at that point. So that's where I decided to extend a bit the structure that I was using to load those messages, and created a dedicated message structure with this time tag and the string that I wanted to send. So then I updated the queues to send those messages. And yeah, that was another point where I made an interesting note, which was that I explicitly disabled the copy constructor here in my message class, because I don't want to do any kind of copy. I just want to be able to create a new message and move this message. But it turned out that in the concurrent queue implementation, there is still a location where you need the copy construction, and that's in the unqueue bulk, which I mentioned just before. So it was this one, this call here. So basically, whenever I was done using the string on the logger thread, and I wanted to send the string back for them to be used on any thread, I would make a copy of the string. Not good. So I think I tried something else on this. Yeah, I was trying to be sure that I was actually copying the string, and it was, so not what I wanted. And okay, I was thinking I could handle that differently, like implementing a copy constructor that would actually move the string itself. But then, before I go that way, I had another idea, which to me seems to be the best path currently. Introduced at that point the message array. And the message array is simply that you have a static string array like that, and you have a fixed capacity for this array, And this is just allocated on start, in fact, on start of the application. And then what you're going to pass on the queues, so the message queue and the recycle queue, are the simple structure, a message tag. And the message tag is simply going to tell you, okay, you have a time tag to orders or some different messages as before, and you also have an index, and the index is going to give you the slot number in the static message array. So what you effectively have here is you start with a slot number, slot 0, and this is bridging a link with a string object which is contained in this array. And you can use the string to reserve some space for the allocated memory, write data in the string, and then you send the message tag on the message queue for processing in the log thread. Then on the log thread, you collect this message tag, and this is a very minimal structure, so you can have a copy constructor or a move constructor. It really doesn't matter anymore at this point. And yeah, that's why you don't really need to bother. It's probably just making a copy whenever you are sending that. And once you collect that on the once you collect that, just like on the logger thread, you will read the data that you have in the string, and then you will just send the message tag object back on the recycle queue, which means that next time you will retrieve that on the recycle queue from any thread, that would mean that the corresponding string slot is free, and you can use it to add some additional data that you want to log on the logger thread again. So yes, that's what I did here. One of the key aspects also is you maybe don't want to have all the all the slots available at first. I mean, it's the best way, not sure. Anyway, so what you're doing here is you check if there is any pending message tag to recycle, and if there's not, then you first check what is the current number of in-flight message tags, because you have a limited number of strings where you can store data now, because this array is fixed and you can't really reallocate that dynamically, and all that would mess a lot of stuff. So you need to keep this limitation into mind. So we check what is the current number of string in flights, and if we have not reached the full capacity of this array yet, then we just start using another of those free slots. And but yeah, we start using another of those free slots here, because we just increase the number of strings in flight. But in the other case, in case we have been using all the slots, then you need to wait, in fact, because you can't use another string slot. All of them are in use, so you need to wait a little. The good thing is, in theory, this should not happen, except if you're really bombarding your message queue so quickly that you're filling all the slots. But I don't think I could reproduce that myself. You could still, if you just messages like crazy, I guess. But this is working pretty fine for me, so I thought that I could to give you some explanation on that, because I think it's a pretty interesting way of doing things. And yeah, this is it. What else did I change? Yeah, finally, I also did another interesting move on the thread local storage, because as I said, there was this get output string which I mentioned before. Where is it? It's this one. This one was supposed to provide you a single string per thread, and as I said, I was using a map initially to provide the string. Except that that's not so good, because in fact you are bypassing some of the consideration that you need to make on field safety, so not good. But then yeah, I eventually introduced this thread local storage, and in this storage I have now a memory buffer and a string. And so if I go and try to find get output string, now when we do that, we just return the corresponding thread storage data. And the other version was this one, reading the ID, trying to find the corresponding string, and if you could not find anything, then you would add a new string with a lock on the map itself. It's an unordered map, and I thought that it would be enough to have a lock here, but that's a point where it's in fact incorrect. You really need to have the lock before you try to find anything, because you could be trying to find something while also adding a string from another thread here, and that would break. So this implementation is indeed incorrect, so not to be used. And it turns out that using the thread local storage is in fact way faster also, so very good to do. And this allowed me to save and improve some of the performances on the log outputs. I don't know if I have any indication on that. Yeah, no. Okay, I didn't provide any actual measurement of the improvements, but yeah, it really feels like it's improving a bit the performances. So I think I have covered everything I wanted to cover concerning this log manager implementation. Apart from that, as I said in the previous recording, I'm still working like crazy on re-implementation of many of the base classes needed for the terrain rendering part in ProLand. Still work in progress, but hopefully next time I will have something to display, at least maybe corresponding to this minimal terrain symbol here. So yeah, we'll see. And for now, okay, so this is it. Thanks for watching, and see you another time then. Bye bye.